As a final example, let us consider a very important circuit element called transformer. What does a transformer do? It is actually used to change the voltage and current ratio, right. So, it has a primary coil which is carrying a current of I1 and is wound by turns N1, and then there is a secondary which is carrying a current of I2, but there is a winding of N2, right. And what would happen to the B field? The B field will actually be completely contained in the core of the transformer, provided that the transformer core is having a large permeability. Okay. So, if you have a large permeability, then B will be uniform upwards inside the core, and the voltage that is produced or the EMF that is produced in the first or in the primary will be the amount of magnetic flux that is changing within that, right. And for the voltage that is produced or the EMF that is generated in the second coil will be minus N2 d psi m by dt, where psi m is the magnetic field that is linking circuit primary coil and the secondary coil, right. So, with magnetic field assumed to be uniform, right. So, you can imagine that if I am applying the current I2, then there will be a current I1 that would be generated, right. So, you can actually see what is the ratio of V1 by V2, and the ratio of V1 by V2 will be N1 by N2, right, and V2 will be equal to N2 by N1 into V1. Normally we are concerned with transformers which are given by 1:n, right. That is to say, the turns ratio is taken in such a way that N2 by N1 will be equal to small n and n will be larger than 1, so that V2 will be equal to some n times V1. In this case, the transformer is actually acting as a voltage amplifier. Okay. On the other hand, if the transformer ratio is specified as n to 1, then V2 will be equal to V1 by n. Okay. In this case, it would actually be acting as a attenuator. A real transformer has a lot of complexity. It has surface currents and it has mutual inductance. We are neglecting all these effects. Okay. For a lossless transformer, however, the total power must be conserved. V1 I1 must be equal to V2 I2. This also gives you a result in terms of I2 by I1. Okay. I2 by I1 will be equal to V1 by V2, which is equal to N1 by N2. Okay. And if you define V1 by I1 as the resistance of the primary and V2 by I2 as the resistance of the secondary, then this primary and secondary resistances are given in the ratio of primary to secondary ratio is actually given by N1 by N2 square. Okay. And if you take a 1:n transformer, then this would be 1 by n whole square. Okay. So, this was about transformer, and again what I want to emphasize is that transformer works on Faraday's law. Okay. The magnetic field associated would be changing. Here, see, what is common about all these examples is that for the transformer or for the coil that is kept with non-homogeneous or homogeneous magnetic fields, the coil was not actually moving, right. The coil was not moving. Okay. It was the magnetic field that was associated with that coils or the wires that was actually changing with time, leading you to some EMF produced. Now take the other case. In the other case, which is called as motional EMF, okay, motional EMF is because of the movement of a wire. Okay. Consider north and south poles, okay, of a magnet. So, this is a north pole and this is a south pole of the magnet. So, there will be magnetic field in between, right. So, there will be a magnetic field. Now, what I do is I take a loop, okay, of some length L and some width W, okay, and then I connect this loop to two brushes which are called as commutators and slip rings, and I connect these commutators to a battery. Okay. I connect this to a battery. I have not really written down nicely, and if there is a battery or a voltmeter, more precisely if there is a voltmeter here, this voltmeter would actually register a reading. When will it register a reading? It will register a reading when the loop is actually moved. You could actually move this loop by hand, taking mechanical motion. You can actually rotate the loop, okay, with a certain angular velocity, and when you do that, there will be an EMF induced. Okay. The EMF induced is called motional EMF, and it actually comes because there is a magnetic force acting on the electrons that are carrying this current. Okay. So, if there is a current I, either you can supply the current I by connecting a battery here, or you can remove the battery and put a load resistor. Okay. So, in one case you are actually generating DC. So, in this case when you put a load resistor, you are actually generating DC voltage. Okay. The commutators are actually chosen in such a way that when this happens, when there is a half rotation of the coil, the commutators actually switch places in such a way that the overall direction of the voltage would actually be in the same direction. Otherwise the voltage would be 180 degrees opposite to the original voltage. Okay. You would actually get an AC voltage, but if you want to get a DC voltage, you flip the commutators at a right time such that the voltage polarity is always unidirectional. Okay. So, how do we understand this motional EMF? Imagine that I have, the loop is at an angle theta. Okay. So, the loop is at an angle theta and there is a torque on this loop, correct? If this is a current carrying wire or the loop, there is a magnetic moment and the torque is given by mb sin theta, and in this case the length of the magnetic element is also need to be considered. So, the torque is r cross f or m cross b, right. So, it would be mb sin theta, and what is m? M is the current times L into W, right. So, this is the torque that is applied on the electrons or applied on the charge carriers, which will sustain the current. Okay. So, this torque can also be related to the work that is required. Okay. And you can find out what is the EMF that is induced, because the torque is given by ILW sin theta, and if the loop is actually varying with an angular velocity of omega t, then the torque induced will be I, and LW can be written as A. Okay. So, I have B sin omega t, and if instead of one loop you have multiple loops, you have n loops, this would be the overall torque. Okay. So, if you have the torque here, now instead of talking about torque, let us look at what is the force that is acting on the charges, right. So, from the torque what we observe is that torque is actually proportional to sin omega t, and this you can see that at some point at omega t is equal to 0 or not really 0, because you are starting something at 0, but at any integer multiple of pi and so on, the torque will actually be equal to 0. Now, torque is a rotating motion, right. So, torque actually causes the coil to rotate. When you supply a current and then the torque make the loop rotate, the loop is actually rotating. So, it is trying to convert the mechanical energy of rotation into the EMF that is induced onto the loop. What we have seen is that if you start the rotation and leave it, then this torque because of the magnetic field actually causes the loop to rotate, but at some point the torque is 0, right. So, when the torque is 0, the battery terminals are actually momentarily shorted because there is no EMF produced and the battery terminals are momentarily shorted. However, because of the initial build up, the moment of the torque where it is actually 0 is very small, and it is actually, it will go over the rotation energy will actually go over the torque and flip the loop. Okay. So, that is what, even though torque is supposed to be 0 at omega t is equal to integer multiples, right, multiples of pi, this will be only momentarily, okay, before it actually overcomes this rest position. Okay. So, the torque actually is sort of continuous except for that brief moment around pi where the torque is actually going to 0, but although that happens, that does not really have too much of an effect on how the voltage is actually induced on the load resistor. Okay. Now, to understand what is the motional EMF or develop an expression for the motional EMF, let us go back to the magnetic force acting on the charges, right. So, with the positive current in this direction which I have taken, and I am assuming that the current is all positive charge carriers, okay, the magnetic force acting on the charge carriers is QV cross B, right, where V is the velocity with which the charges are moving. In this case it is the angular rotation, right. So, you need to connect this velocity to omega, right, omega being the angular velocity in turns or radians per second or just per second, and V is the linear velocity. So, you have to connect V, omega and L and when you connect that, you can actually see how fast or how quickly the charge q is moving, and this force acting on that charge will be given by q v cross b. Okay. So if you now take this force and then say that the loop goes over over a small distance, right. So initially let the loop is at this angle theta, call this as theta 1, okay, and then let the loop be at an angle which is, say, I am trying to write down a loop here, okay, a loop with a resistance up here, let the angle here made be theta 2. So initially I have an angle theta 1 and an angle theta 2 now after a movement of the loop, right. So in doing so, it has actually moved a small distance of dl, right. So what is the work done on this current loop, so that it has actually moved a distance of dl, and that work will be force into distance, right. So Fm being qv cross b, when you take this and then integrate over the small distance dl or multiply this one with dl, and you have to keep in mind, because these are angles, I mean these are vectors, you have to use a dot product over here. So force into distance will give you the work that is done. This is the differential amount of work done by the magnetic field in order to move the charge in such a way that there is a movement of dl, right. So it is actually pushing the charge, the torque is actually being applied over here to rotate the charges, right. So what would be the total work done? Total work done will be qv cross b, so q actually applies to both v and b, dot dl, right, over the complete loop. Over the complete loop, this would be the work that is being done. Now I know that work done per charge gives me the potential or the EMF, and therefore this EMF is given by v cross b dot dl. Okay. This would be the closed loop integral, and this integral which you have obtained is called the motional EMF. This EMF is different from the changing magnetic field, okay, getting linked to the corresponding circuit and producing a EMF. So this EMF, which is sometimes called as the transformer EMF, because here the coils are stationary, it is the magnetic field which is changing with respect to time, and this EMF which is called as a motional EMF, in which the magnetic field is stationary, that is magnetic field is uniform, it is not changing, it is always B0, whereas it is the coil which is actually moving. Okay. This example was that of a DC generator. One can actually make an AC generator also out of this. In a typical DC generator, there will be multiple loops. These loops are called as armatures. There will be multiple windings of the armatures. Okay. Here I have shown only one wire. Otherwise, you need to multiply everywhere by value of n. Okay. So here is the number of armatures. So there is actually a distinction to be made between two types of EMF. One EMF is called as the motional EMF, the other EMF is called as the transformer EMF. Technically these two are distinct phenomena. Okay. One phenomena can be explained without using Faraday's law at all. The motional EMF does not require Faraday's law. Okay. However, it is possible to view this as a special case of Faraday's law, so that we do not have to deal all the time with motional EMF and transformer EMF. Although the subject of which one is motional EMF and which one is transformer EMF is very interesting, and there are a lot of paradoxes associated with that. Primarily, which motive, which agency to apply, or which agency to actually consider as the one that is responsible for producing an EMF in circuits. Okay. There are a lot of interesting and paradoxical situations where it is not very clear which one is really operating. Fortunately, it turns out that whether this is motional EMF or transformer EMF, the net result is that there will actually be an EMF induced. So if you just think of how the EMF is, if you just think of the EMF induced and do not distinguish between motional and transformer, then you will be fine. However, in most cases it is very difficult to determine, because there will be component of motional EMF as well as transformer EMF. Okay. And Faraday's law has been extended in such a way that both can be considered as special cases of Faraday's law. Okay. In the case where transformer EMF is there, the magnetic flux that is changing is because of the changing magnetic field, right, or the loop is stationary, right. You can move the partial differentiation inside and say that this minus del B by del T, which is changing and being integrated over ds, is the one that is responsible for EMF induced. Okay. Motional EMF can be sort of incorporated into Faraday's law if you keep this minus d by dt outside and then let the surface change over. Okay, so if what it means is that the total flux linking would actually be changing, right, with respect to time. So in this case of DC generator, the total flux will be LW into B0, but that would not be constant, that would be changing, right, because the surface itself is changing, it is rotating, there will be a factor of sin theta into there. So both methods or both interpretations will give you the same EMF, but it is true that motional EMF has actually nothing to do with Faraday's law, only that we have considered Faraday's law so that extended Faraday's law so that it can be motional EMF can be absorbed into it rather than dealing all the time with motional EMF. Okay. We will not be dealing with this motional EMF in this course, in fact we will not even be dealing with transformer EMF. What you have to realize is that Faraday's law simply states that there will be a EMF induced whenever there is a changing magnetic field, okay, and EMF is electric field. What if electric field is also changing? That is an interesting question, we will come to that question later. Okay. So now we want to develop point form of or differential form of Faraday's law. Okay. So I want to develop this one because I want to complete Maxwell's equation. So this is the third Maxwell's equation that we are looking at. We have already relation which says del cross H is equal to J, right, the current enclosed or the current density J, and then we have del dot B equal to 0, del dot D equal to 0. We also have del cross E is equal to 0, right. We had del cross E is equal to 0 because this was for the electrostatic case. However, we have seen several cases where del cross E is equal to 0 may not exactly be true, and this is one of the cases where it is not true. Okay. So we begin again by writing down what is EMF. EMF around a closed loop is E dot dl, right, over the closed loop is E dot dl. So here del dot D is actually rho v, which is the volume charge density. So coming back to the EMF that is generated, EMF is given by the line integral of the electric field, right, over the closed curve C. So it is integral of E dot dl, this should be equal to minus integral of del B by del T dot ds, correct. To develop the point form, you need to see that if you take integral of E dot dl over the closed curve or on a short closed path and then divide by ds, what you are going to get will be whatever that is there on the right hand side, right. See, I will not develop this one in the detail that we developed it for the magnetic field. Okay. We will go by the analogy between these two equations. So in these two equations, if you see, the left hand side is a closed line integral of a corresponding vector quantity and the right hand side is an open surface integral. Okay. And if you now write down the point form for this integral of h dot dl equal to integral of j dot ds, the left hand side can be rewritten as del cross h dot ds, right, over the same surface. This would be equal to j dot ds, and from here we wrote that del cross h is equal to j. This was by making use of Stokes theorem, right. Similarly, I can write down for the left hand side of this one as curl of E, right, after integrating over the same surface or applying Stokes theorem I will get the same thing. So curl of E will be equal to minus del B by del T. Okay. So clearly the equation that we were using earlier, del cross E is equal to 0, is no longer true because there is magnetic field that is present and this magnetic field is the source of the EMF. The changing magnetic field is the source of the EMF, and therefore this equation had to be modified from the electrostatic case, and this is the point form or the differential form of the equation for Faraday's law. Okay. And this equation is valid for time varying as well as time invariant cases. When time is not varying or when the fields are not varying with time, then the right hand side will be equal to 0, which means that electric and magnetic fields are separately considered. There is no interaction between the two. However, when the magnetic field is changing, it will act as a source of EMF or it will act as a source of the electric field, which means that they are now related to each other. Okay. We want to develop one additional form for the electric field, which is interesting because we have seen that electric field is equal to minus gradient of V earlier, right. For the electrostatic case, we were able to write this electric field as minus gradient of V because del cross E was equal to 0. Okay. This was for the static electric field case, we were able to write this one. But now del cross E is no longer 0. In fact, this is actually equal to minus del B by del T. So can I still write E as minus gradient of V? Turns out that I cannot do this, right. In the general case, I cannot consider the electric field as a gradient of a time independent potential. The physical reason should be quite obvious. This potential function V was independent of time, it was only function of spatial coordinates. So no matter how or what operation I do on this V, I will never be able to get the time variation. So clearly this equation needs to be modified. So how do I modify that equation? Let us go back to the Faraday's law, right, in the integral form. So write down this as integral of E dot dl, which is the EMF produced, given by minus del by del T of B dot ds. Okay. Now I know what is B in terms of the vector potential A. So B is equal to curl of A. So I can write down this as minus del by del T. I can pull this minus del by del T outside of the integral and have del cross A dot ds. Okay. I can also push this del by del T inside and write this as minus del cross del A by del T dot ds. Now I have one line integral, closed line integral and a surface integral. I can actually convert one of them into a same integral by applying Stokes theorem. So I can convert the left hand side into writing this as del cross E dot ds, curl of E, which would be equal to minus del cross del A by del T dot ds, and push this into the left hand side, you get del cross E plus del A by del T dot ds over the integral will be equal to 0. This simply implies that curl of E plus del A by del T is equal to 0. Now I seem to have obtained a new type of an electric field, right. This new electric field actually is the old electric field plus the time variation or the rate of change of the magnetic vector potential itself. Okay. So for this new field, curl of E nu is equal to 0, which means that E nu can be expressed in terms of gradient of a scalar potential. Okay. Thus you can actually rewrite electric field as minus gradient of V minus del A by del T, and this will be the general expression for the electric field, having a spatial dependent form only when the time variations are 0 and the time variation included. Okay. So this is the expression for electric field in the most general case. Okay. So you have a time independent parameter and a time dependent parameter. When there are no time variations, when there are no magnetic fields, you will have only the gradient of the potential. When there are magnetic fields, obviously this would not be the same thing. Okay. So this is about the electric field in general in terms of the potential. Okay. So let us consider one example of point form of Faraday's law, and then we will stop discussing Faraday's law. Okay. So the example that I would like to consider is that B field is given to be some uniform z hat, okay, and B0 e to the power minus alpha t. We have already obtained what is the induced EMF for this case, right. We have seen that the induced EMF is positive and it has a current in a particular direction for the loop that we have obtained. What we want to find is determine the electric field E. How do I determine the electric field E? I know from point form that curl of E is equal to minus del B by del T, right. So if I differentiate B with respect to time, I get alpha, there is a minus sign, so therefore that minus and minus sign will go away. So I get z hat alpha B0 e power minus alpha t. Okay. So this is the curl of electric field, okay, and you have to now apply the curl operation in the appropriate geometry. Remember, the geometry that we were considering was the cylindrical geometry, right. It was actually the loop that we were considering, or you could think of this as a coaxial cable with the magnetic field coming out in this way, okay, and the magnetic field will be given by this expression. So it does not really matter, you have to think this one in terms of the circular loop, and if you write down what is the expression for curl of E, you will have 3 components R, phi and Z, but clearly because the right hand side has only the Z component, you will have to have only the Z component for curl of E. Okay. The Z component of curl of E will involve ER and E phi components, okay, appropriately differential with respect to phi or differential with respect to R, right. There would be a 1 by R or minus 1 by R that would be there, but point here is that you have radial electric field component and phi component here. Clearly Ez will be equal to 0, there will not be any Ez possible in this situation because the right hand side is, I mean the curl of E has only this component, right. Now amongst the radial and phi component, by symmetry of this problem, because I know that the loop is symmetric around phi, right. So the loop is symmetric around phi, azimuthal symmetry, but if I change the loop radius, then the value of the EMF induced will change because the cross sectional area will change, right. So clearly I should have E phi component and this should only be a function of R, okay, and for that you can substitute for the values. So you will probably get something like del E phi by del R is equal to alpha B0 e power minus alpha t, and calculate E phi by integrating this expression, okay, over whatever the value that you want to. Just integrate this expression, you are going to get alpha R B0 e power minus alpha t, okay. This I am assuming that my expression for del E phi by del R is correct, otherwise you have to actually put up the proper value for del E phi by del R, proper expression for the curl of the electric field, and then find the electric field, okay. Just to sum up, the electric field will be along the phi component. Do not exactly worry about what the actual value of the electric field is, okay. This can be done if you know what is the expression for curl of electric field, okay. So I have electric field along the phi component, okay, and this was, and I can actually evaluate what is the value of this electric field by using this point form of Faraday's law.